Alright guys, what's going on? So today we are going to be talking about more financial models in physics. So we sort of introduced this concept in our earlier video last week where we were talking about we were talking about arbitrage, local transformations, global transformations, and all that. Today we're going to be putting physics to things. We're going to be sort of identifying very important concepts in modern physics to analogies here in the financial market. Okay, so if you like this kind of content, you can get the long versions of these videos on my Patreon page, or you can become a member here on YouTube. You can also contribute as a member. You can contribute on Patreon also. With that being said, let's just go straight into the topic now. So we're putting physics to things now. And so let's go ahead and do this. We have established that global symmetries of the financial market are rescaling of prices, and this is things like inflation, whereas local symmetries come in the form of arbitrage. Okay. Also, if you want notes, my notes will be going on Patreon as well, which requires exchange rates or connections. Okay. So here's the picture here. So we have global transformations. These things are relative prices. Inflation affect the relative prices between objects or commodities. Local transformations will preserve arbitrage. Okay, and the arbitrage, again, is the ability to make money depending on where you sell and buy from. Okay, but the caveat here is that we need exchange rates in order to have this. Okay, in order to have local transformations, we need exchange rates. Okay, so let's start drawing an analogy here to physics. In modern physics, there are two broad types of transformations: global and local transformations. Now, you might say, okay, what about conformal transformations and all this kind of stuff? This is more advanced stuff. Okay, well, we'll get into this, conformal transformations, gauge transformations, all this kind of stuff. Gauge transformations are going to be quite interesting. But broadly speaking, there's global and local. Okay, and we're just going to focus on these for right now. Global transformations do not depend on time or space, whereas local transformations do. Okay, so you might see something like, if you're new to physics, you might see something like a global transformation might be, again, it's not a function of space and time, so you might have some Lagrangian plus some constant, okay? Whereas a local transformation is going to be some Lagrangian plus some constant, and that constant depends on where you are in space and time, okay? So pictorially, we can look at this as, suppose we have a sphere and we move everything on that sphere by some constant, okay, and that constant is this e to the I theta. This is a complex number, it's a complex constant. This thing, we can rotate the function on the sphere all by some complex constant. So this is going to be like, say, some 90-degree rotation in the sphere. Whereas in local transformations, this is a little bit different, right? So not every single point is going to be rotated by the same value. Every single point is going to be rotated in some way that depends on a transformation that is located at each point, right? So a global transformation makes this look like nothing happened, whereas a local transformation in this case does make it look like something happened. And so in order to find the invariant quantities within local transformations, we need to dive into this a little bit more. And we're going to be able to understand fiber bundles, and we're going to be able to understand the really deep things about local transformations, specifically gauge transformations, that are going to be quite illuminating and useful and interesting. So the amount of money that some object is tethered to, an orange, for example. So we talked about oranges, bananas, and apples in our earlier video. We're going to say lives in some internal space. Okay, and this is really, really important because this permeates everywhere in modern physics. So this is to say that the price of an orange doesn't depend on where the orange is or how old it is, right? So the internal space or the value of the orange fluctuates by its own volition, okay? In physics, internal spaces include charge, spin, and color, okay? Charge, if you're not new to physics, charge is going to be associated with U1 transformations. Spin is going to be associated with SU2 transformations, and color is going to be associated with SU3 transformations. But we're sort of stepping beyond our bounds here. Let's just take a look. This is some geodesic. Okay, and my apologies for the dog barking again. Suppose we're riding on some geodesic, some particles riding along some geodesic, and along that geodesic, that particle could have spin up or spin down, and that spin up or spin down doesn't necessarily depend on where this particle is along that geodesic. It could be random, it could be whatever, right? And so here's our spin, right? So our spin arrows just are these things, just to pictorially try to understand what's going on here. In the example from our last video, we looked at Germany's situation and gathered that it would be beneficial for Germany to buy oranges from Britain and sell to Italy. Okay. This arbitrage that Germany has is a driving feature of something deep in physics that relates to an anti-symmetric tensor, which is what we're going to derive now. Okay, and this anti-symmetric tensor is going to be very, very important later when it comes to sort of quantifying this arbitrage. Okay, we're going to start by overlaying a grid on top of our countries, and we will take France to be at the origin for the sake of Cartesian convenience. Okay, so here's our grid. We can define vectors at some origin, emanating from some origin, okay? And this vector, so this vector here, from here to here, is going to be our n vector. This vector from here to here is going to be n plus some direction in the y, or some unit vector in the y direction. This one here is some unit vector in the x direction. This one here is unit vector in the y direction plus unit vector in the x direction. Okay, so we have 4 vectors, all denoted in this way. Okay, let's continue. So we're dealing with strictly values of oranges here. In this case, so that to make the picture slightly a little bit more accurate with what we're talking about when we attach vertices to prices. Okay, so again, just oranges. We're not going to be talking about bananas or anything like that, or apples, for the sake of simplicity also. This is an important distinction. So we want to attach vertices to prices, not commodities to themselves. This is an important distinction because there's a difference between the value differences in the actual flow of goods between countries, and we're sort of getting to that point. We're going to be able to understand how objects flow from one country to another, how we can quantify that. That's going to be associated with some flux. Okay, but let's put some more symbols to this. So we had our vectors, right? So vector n, this vector, and this vector, located at each point within our vertex. Okay, we've slanted this just a little bit, but just suppose for the sake of argument that this is our flat Cartesian system. Okay, so we can see as we go from, let's say, France. So suppose we're starting here in France, prices in France. Okay, and then we go to prices in Italy, right? When we go from here to here, this vector is going to be described in this way, okay? This is a sub I of n. Okay, forget about now what the sub I is. We'll say that the sub I refers to the direction it's traveling. So I is going to be in the x direction. J will be in the y direction. Okay. So we're going from, and this is from n, coming from n. Okay. This one here is coming from n plus ex. Right. So this vector here. So we can actually do this, right? So we can say that vector, and then we have this vector, and then this vector here is going to be this guy here, and then this vector here is going to be this guy here. So what we've really done, right, is defined 8 vectors, right? So 4 vectors over here, and 4 vectors over here. I'll number them, right? So 1, 2, 3, and 4. The orange and red vectors are difference vectors between 2 of the others that we defined in the previous image and represent the exchange rates, right? So we have vectors that represent prices, those are these blue ones, and then vectors that represent exchange rates, which are these colored ones, these ones. We can construct a mathematical object then that represents the net result of all the exchange rates going in one full swoop, or in one full circle. And that object is going to be this Fij, okay? So, the exchange rates, let's just look at this. Aj, this guy here, is going to be this guy right here. And this guy here is this guy right here. We have a minus sign because we're going in the opposite direction, okay? And then we have a minus sign here, right? So this guy here is this guy here. This is going, then we'll say this is the negative direction. So say that's negative direction. This here is the negative direction. This here is a positive direction, and then this guy here is going to have a positive direction also. So just for directionality purposes, this is positive and negative. Actually, no. So going up and right is positive. Going left and down is negative. And so when we look at that, we could see, okay, we have, we can make sense of these minus signs now. Because minus makes a plus, and that's a plus sign right here. This new object, known as the gain factor, this is how much we're going to gain from any country. In this case, we're looking at France, but we can do this for Germany as well. But this is the gain factor, right? So in electromagnetism, this is going to be the electromagnetic field tensor. But in economics, we'll call it a gain tensor, okay, or a gain factor. So, electromagnetic field tensor, electromagnetic strength field tensor. And there's an equivalence here between the gain factor and the electromagnetic field tensor. This thing here is physics. So physics. This thing here is economics, right? Let's call that economics. This new object is the gain factor in economics, and it can be seen to represent the net benefits that a country will receive upon arbitrage. In physics, this can be thought of as a matrix, but because it's constructed by exchange rates, which are independent of local transformations, F is also independent of local transformations. So, this object here is independent of local transformations. Okay, so this thing And this sort of gets to the concept of gauge transformations and gauge theory also. We're not going to go too deep into that, into this video right now, but keep that in mind, because we will come to it later. In the continuum limit, this isn't difficult to see that we can take this object here, right? So that's this right here, and this object here, which is this right here, and say that, so this is like a derivative, right? If we just divide this, if we divide this by a, divide this by a, this is really just looking at this. We don't even have to look at this. These are just definitions of derivatives, but just looking at this looks like a change between two things, and so if we come to the continuum limit, this could be thought of as a derivative in some direction, right? In the EI direction, right? So in the XI direction, and this is a J, right? So that means this guy here is this, and this guy here is this one, and so we can construct Fij to be equal to this. And this is the definition of the field strength tensor that we all know and love in physics. If you're new to physics and you don't know this equation, you're going to have to, right? So we've derived this thing from a financial perspective, okay? And let's continue. So we can note that the number of entries of A is equal to the number of trading partners with Germany, okay? So in physics, this is actually a lot easier to understand in physics, right? Because Xi, I and J refer to X, Y, Z, and time, right? So we can, so if we're taking for an example F, T, Y, well, this is going to be D, let's erase these guys. This is going to be dx, or dt, actually. Let's see. A, y, minus d, dy, a, t. So these are components of A and with respect to derivatives. Okay? So that's just an example. We can calculate the flow of oranges between Germany and Britain, for example. Now, so when we do this, so we can talk about the actual flow of goods now. Now that we have this object, let's consider now the flow of oranges from Great Britain to Germany. Okay, Germany's going to pay Great Britain, and Great Britain's going to give oranges. Right? So let's take this now and expand upon this. We can say that the price of the orange in Germany is Pn, right? So this is price. The price of oranges in Britain is Pn plus EI. Okay, so we're going in some direction, in the EI direction, and the exchange rate between Germany and Britain is this thing right here. Right, so the price here is this guy, the price here is this guy, the exchange rate is going to be this guy. We can then define the gain factor in this case as being the ratio between the final amount of money gained to the initial amount. So the gain factor is going to be this thing, all right, which is this, divided by this here, right? So this is the amount, this is the final amount of money gained in Great Britain to the initial amount, which was the price here times the exchange rate. Okay, now we're going to do a little bit of math, sort of physics manipulation here. We're going to say we can exponentiate G, right? So that this guy, we're going to define this. We can also exponentiate these functions here, right? So e to this power is going to give us this, and then we have e to all this. So we're just exponentiating both sides, right? So this thing here is then going to be this, just by the property of natural logarithms, or the e function. It's going to be this minus this times this, right? And so let's see. No, it's going to be this minus this, right? Because this is 1 over e to the a also. Okay. This h is still the gain factor. It's just an exponentiated stand-in for the gain factor that we originally started with. What we can actually do here, I think, let's just go here and then I'll come back up to here really quick. This will define how lucrative orange trade is for the buyer. Okay. In other words, it stands for how much Germany stands to gain during this transaction. What is driving the flux of the commodity is the exchange rate as well as the prices of the oranges on both ends. We could see this as exchange rates laying down slopes and the prices as setting the direction that the slope is going to face. Okay? So this is how I'm sort of picturing this, right? So the exchange rates lay down the slopes. So if you have a very very steep exchange rate, for example, the slope is going to be very large. Okay, it's going to be a huge slope, say, for example. And the prices as setting the direction in which that slope is going to face. Okay, so if we know the exchange rates and the prices, we can calculate the flux of the commodities between the countries. Okay, so you can almost sort of imagine this as the commodities falling down these slopes. Okay, and these slopes are defined by the prices in both countries and or the prices of the commodities in both countries and the exchange rates between the two, because you need to know both in order to know the direction of the flux of the commodities between the two countries. Okay, so you need to know that how steep the slope is, and you need to know which direction the slope is facing. Okay, the steepness of the slopes is going to be given to us by the exchange rates, whereas the direction is going to be given to us by the prices. And generally, you want a country. It would be beneficial for a country to gain the commodity. So they would want an exchange rate that is, say, high, and facing towards them. Okay, let's keep on going here, because my mind goes a little bit abstract in this way. But the exchange rates are vectors because they point in some direction. Okay, they're going to point either in the direction of Germany or Great Britain. And the prices are scalars because they're just numbers. Okay. Okay, so looking at the gain factor, we slap a constant in front of that. Okay, so we slap a constant in front of this guy, and we say that, so this is a derivative. We slap a constant in front of all of this, and that converts this lucrativity into a number of oranges. And so the result is an orange flux equation, if you will, or the flux equation, and that's this thing right here, right? So we have a scalar. This is a scalar. These are the prices. And then these here are the exchange rates, as we said before. These are connections, right? This is connection. I'm calling them connections because in physics, we're going to call them connections. The gradient of prices along the landscape, along the financial landscape, right? So that's redundant, along the financial sometimes I catch this stuff, sometimes I don't. Along the financial landscape, plus the exchange rates drives the flux of the commodities within the economic system. So prices, you lay down prices everywhere in the world, you lay down exchange rates everywhere in the world, and you can get an idea of what direction commodities are flowing towards, right? So in the United States, a lot of commodities flow into the United States, and that's partly because the prices that we have in the United States compared to other countries are such that when we consider the exchange rates, all the commodities generally tend to flow in our direction. And so it's the same thing with a lot of Western countries, right? So a lot of Western countries, Germany, France, England, United States, maybe Canada, all these places are, they all have the flux of commodities coming towards these places is very high. Okay, whereas in other places like South America, Africa, the flux of goods coming into those countries is relatively low, and that's going to be because the exchange rates are not in their favor, or their prices are astronomically high for anyone to buy within those countries. Okay, so this all fits into our picture that we painted earlier regarding global and local transformations. And here's how. So we had our global transformations. These were our relative prices. Okay, so again, the global transformations, something like inflation, for example, that's going to drive the prices of everything within a country up. But the thing that remains invariant, again, are relative prices between commodities. In local transformations, the thing that is rendered invariant is the arbitrage. So you can tweak the value of the oranges in, say, Great Britain somewhere, but the arbitrage between in Germany is going to stay the same. Okay. Or the ability to make money, for example, in Germany is going to stay the same. And this is only done possible, however, because of exchange rates. Okay, exchange rates. So now we have this exchange rates determine commodity flux when we put the prices of objects into the picture. Okay, so we're building upon this picture. Global transformations, local transformations, and we can see that in local transformations things are quite a little bit more interesting because there's different things at play here that determine invariant properties that are locally invariant, or invariant properties that are local. Okay. All right. Let's start putting some more physics symbols to this, because exchange rates are vectors because they point in some direction. And prices are scalars because they're just numbers that tell us how much something is at any given time. So in physics, we can therefore think of exchange rates as vector fields, okay, and prices as scalar fields. So our exchange rates are vector fields, so they're vectors at every point in space and time. And then we have prices, which are scalars at every point in space and time. In physics, the arbitrage equivalent are the things that remain invariant under local transformations. So with the help of particles that represent exchange rates, so let's take our map of Europe and convert it into a map of physics. So here's our little mini map of Europe. We have local transformations driving some prices somewhere, down or up, in this case down. And these local transformations are going to take three forms. U1, this is unitary transformations, unitary matrix transformations. Okay, I'm not going to say matrix because that's a little bit of a misnomer. But we have U1 transformations, SU2 transformations, and SU3 transformations. Okay? Those are the transformations. Okay? The exchange rates are between these countries are going to be facilitated in the U1 case by photons, in the SU2 case by bosons, and in the SU3 case by quarks. And the arbitrage for each one of these special types of transformations is going to be electric charge in the U1 case, isospin in the SU2 case, or spin if you just want to call it spin, and then color charge in the SU3 case. All right, so this is what we got. I haven't really talked about the difference between these things yet, but all this really comes down to is Lorentz transformations. And their representations. Right, and so these are three different representations of the Lorentz transformations. And nothing's really stopping us from getting other representations, right? We could have SU5 transformations, SU6 transformations. And generally when we talk about like U5, for example, SU5, this is when we start talking about grand unified field theories, right? So GUTs, for example, grand unified field theories. We are probably not going to talk about that in this playlist. However, it is something that I do want to talk about. But we can now sort of see, like, okay, if you can understand finance, you can understand modern physics, right? So don't be scared by modern physics. Don't be scared by all the symbols and all this stuff. If you can understand finance, if you can understand the financial market, if you can understand global economics, if you can understand micro and macroeconomics, we can be able to understand a lot of these concepts in modern physics as well. Okay. Keep in mind also, there's something interesting also to note is that when we considered local transformations, I think it was this video, might have been the other one. When we considered local transformations, right, let's go to this picture here. When we considered local transformations, we were talking about, we had to zoom out. We had to take a look at a bunch of different countries, right? So this can be thought of as the macro. We need to have a macroeconomic understanding of things. Whereas in global transformations, you can just look at like one country, or you can look at like the United States, for example, or even more more local, if you will. This is a little bit of a weird concept, right? But there's for global transformations, this would be more economics. So microeconomics and macroeconomics, there's sort of this trade-off, right? If you want to talk microeconomics, it's probably beneficial for you to talk about global transformations, because things like inflation, anything that happens, any political unrest within a country or something like that, that's going to affect the value of currency within that single country, right? And so that country encompasses a large space, right? And the value of currency within that country is going to go up or down, right? Whereas when you start considering countries that have different exchange rates, or that have exchange rates with one another, then we could start talking about macroeconomics. So there's this weird balance here between macro and microeconomics and global and local transformations. And so with that being said, I hope you guys like this type of content. Make sure to hit that like and subscribe button. Make sure to go into my Patreon page if you want to support the channel or become a member on YouTube as well. You won't be just supporting the channel. You'll be getting longer content. You'll be getting more content as well. And so with that being said, I will see you guys in the next video. Bye.